Hello, my name is Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And this is a continuation of our AVR assembly language lectures where we talk about loops and conditionals. And just by way of introductions, when we talk about loop statements, we're referring to while loops, for loops. Conditional statements, we're talking about if-else statements. And the thing that both loop statements and conditionals have in common is that they require us to execute instructions in different locations of instruction memory. So depending on, for example, if an if statement is true, we might execute a certain series of instructions, and if it's false, we want to execute a different series of instructions. And that means we need to hop to different places within instruction memory where we can find the instructions that we want to execute. And this is implemented by changing the value in the program counter. And we talked about this a little bit already in our discussion of branching when we were designing our microarchitecture hardware. And with the different instruction sets treat branching differently, but with the AVR instruction set, branching is, and conditionals are sort of created or performed using two assembly language commands. So the first command is the compare or CP command, where you compare the values in two different registers, and based on that comparison, some of the ALU flags might be set. And then once the ALU flags are set, then we immediately follow the compare statement with a branch command. And there are a variety of branch commands. So we can have BREQ, which is branch if equal. There's branch if not equal, there's branch if less than, branch if greater than, and you can check out the AVR instruction set manual and you'll see a complete listing of all of the different branch commands available. The one thing that all of the branch commands have in common is that they require an offset. So if the branch condition is satisfied, then the program counter is changed with a new value. And typically it's changed by adding an offset to the program counter. And this basically causes us to jump to a different region in instruction memory. Now this offset can be a number, so you can literally follow a branch equal statement with a number positive 10 or negative 20, something like that. Or you can use a text segment label. And remember, a label is an alias for a location in memory. We've seen labels used both in the data segment. Now we're going to use them in the text segments. So what I want to do first is I'm going to quickly, pretty shortly here, switch over to the MPLab environment, and we're going to write some assembly language code that implements an if-else statement. And this, we're basically going to implement this bit of C code. So if we look at the C code, we've got two variables, A and B. And if A is less than B, we increment A. Otherwise, we increment B by 10. And then once we're done all that, then we increment A by 1. And so I'm now going to switch over to the dev environment and implement this in AVR assembly. And I would recommend while you're watching that part of the video, just keep this bit of C code in front of you so you can sort of step through the C code as I'm creating the assembly language, and you can see how the C code maps into the assembly language. Okay, so just to start out with, I'm going to set some register values here to represent our variables. So register 16 is going to represent our variable A. Register 17 is going to represent our variable B. And in our C code, we're going to at one point want to add 10 to something, and at another point add 1 to something. And so I'm going to just create or use some registers to hold these increment values. So we'll use register 18 for incrementing by 10 and register 19 for incrementing by 1. Now, the next thing I'm going to do is I'm going to define a series of, or I'm going to add a series of labels to our text segment. And again, labels are they just represent an address, or they're an alias for an address. And I'm going to actually have 3 labels. I'm going to have a label called Conditional Test, which is going to start the test for our if statement conditional. I'm going to have another label called if true, and as the name suggests, this will be the section of code that gets executed if the if condition is true. And I'm going to have a third label here called end if, and that's just going to represent the end of the if statement. And so under conditional test, this is where we're going to do our logical test contained within our if statement. And if you'll remember, the test is that we do is whether or not A is less than B. So again, we need to use 2 commands to implement our conditional tests. The first thing we want to do is we just need to compare our 2 variables. Whoops, 16 and 17. And then I'm going to use branch if less than if true. Okay? And so just to expand on what's going on here, so the copy command, as we've already seen, it basically is implemented using a subtraction operation. And so really what's happening is R16 or R17 is being subtracted from R16. And if the value from the subtraction is negative, the negative flag is going to be set, and that indicates that A is less than B. So this branch less than executes if the negative flag is equal to 1. The ALU negative flag is equal to 1. So if branch less than then needs an offset to reprogram the program counter. And again, I could have used a number here. I could have said 12, and that would have literally added 12 to the program counter. But instead, what I'm going to do is I'm going to, just because it's a little easier and it saves me from having to calculate the offset, I'm just going to tell the command to jump to the location of the text segment that matches the if true label. So down here at if true, if you look at your C code, if the if condition is true, then we add 10 to the A variable. So A is R16. We've got 10 contained in R18. And this is A plus equal to 10. So that's the if part of the if statement. Now what about the else part? So the else part is executed if the if statement is false. So where do we put the else statement? When writing assembly language, we put the else statement actually right below the branch statement, because if the branch condition is false, then we just execute the very next command that follows the branch function. And the code that we want to run if the branch condition is false is the code contained in the else statement. So this is where we're actually going to increment the B variable. So it's interesting because the order of the if-else code is actually reversed compared to how it appears in your C program. So in your C program, the if code immediately follows the conditional test. In this case, the else code initially follows the conditional test. Now, one other thing that we need to add is remember that unless we're using a branch statement or a jump statement, what we an assembly, our microarchitecture by default just keeps executing sequential instructions in instruction memory. So once we execute this add R17, oh sorry, this should be R18. So once we add 10 to the B variable, if we add nothing else to our program, the very next line of code we're going to execute is this one. And so we're going to execute our else code, and then we're going to execute our if code, which obviously we don't want to have happen. We want to execute the if code or the else code, but not both. And so the last thing we need to add to our else clause is a statement that will jump over top of the if code. So I achieve that by saying jump end if. And end if is just what happens after the if statement is complete. And if you look back at our C code, the last thing we need to do is add 1 to the A variable. And we just do it like that. And that's our complete code. So, again, if you want, pause the video, make sure that this makes sense. And, if it does, if everything is feeling good, then what we'll do is we'll compile this thing. Oops, I should have add my my breakpoint. Okay, so let's run this thing. Okay, so if we check our, I've got a bunch of watches for our registers. Check those over, you can see that they all make sense. And I'm gonna step through the compare command. So is A less than B? Yes. So we are going to execute the if statement. But before we do that, it's interesting to take a look at the instruction memory, at the actual opcode and machine language instruction values of our instructions here. So we're on the branch less than statement, and the binary machine language instruction is F01C. And if you pause the video and you, well actually, what I'll do first is let's hit that branch function, and you can see that we jump over top of the else code and we land on the add statement at if true. And so in order for that to happen, we needed to jump over 1, 2, 3 bytes of instruction memory. And so if you pause the video and look at the binary content of this branch less than command, F01C, at least it is on my simulator, then you'll be able to go into the AVR instruction set manual, figure out which bits of this command correspond to the offset, and verify that it was the right value to basically jump over 3 addresses and land on this add command. Another thing I want to point out, I think this is the first time that we're seeing this, even though we don't execute the jump command, we can see its we can see the jump command in the instruction set memory, and you'll notice it takes it's actually 32 bits long rather than 16 bits long. And the reason for that is because it stores a full instruction set. It stores the full address of the location in instruction memory that it's jumping to. So it stores the full jump address. And so the command in the in our assembly code is jump end if. So it's supposed to if this jump command is executed, it's supposed to jump all the way down to this final add command. The final add command has address, shows up in instruction memory at address 6A. And if you look inside the machine language, the 32-bit machine language string for the jump command up here, you'll see that address 6A is actually embedded inside the machine language instruction. Again, open up the AVR instruction set manual, take a look at what jump is supposed to look like and how all the bits are laid out, and then check out these values in the opcode column to make sure they make sense for you. This is a really great way to consolidate your knowledge about what's going on with the simulator and what's happening in instruction memory. So all of the values, this column is kind of misleadingly called opcode. It's not just the opcode, it's the entire machine language instruction that's shown in this column. And you can sort of, particularly when you're dealing with jumps and branches with offsets and addresses embedded in the command, you can actually see the proper addresses embedded in the command. And then of course, this column is the actual address in instruction memory. So anyways, that's just maybe a little bit of a side point, but I think still something worthwhile pointing out. Now, if we go back to our program, the last thing we need to do is increment A by 1. We do that, and that is, we do that, and that is the end of our program. So just to switch back to our slides now, this slide basically just kind of summarizes what I've talked about when we were looking at the simulator. So the if condition, or the if test, is actually implemented using 2 instructions, as we've seen. The compare command followed by the branch less than command, which modifies the program counter based on the value of n. Again, you can look at the binary content of the branch less than command inside the simulator to make sure that the offset makes sense. And since jump and branch less than take immediate arguments, the labels that we use are translated by the assembler directly into the required values for those immediates. So branch less than and jump both took labels, right? We both gave them labels. But in the case of these 2 commands, the assembler did different things with those labels. For branch less than, the assembler used the label to calculate an offset, and for jump, the assembler used the label to calculate an actual address that gets embedded inside the machine language code. So that's if statements. Now, the last thing I want to do in this lecture is also take a look at how we would implement a while loop. So here's a simple while loop. We've got variables a and b. While a is less than b, we're going to increment a. And then once we're all done, we're going to set the variable a back to 0. Oh, and I forgot my semicolon. I've been writing too much Python. So keep this C code in front of you. I'm going to switch over to the simulator. I'm going to write the assembly language for this that implements the functionality in this C code, and then we'll step through it in the debugger, just like we did with the if statement stuff. All right, so similarly, or kind of like we did with the last program example, I'm going to use registers to represent our local variables. Our 16 is going to represent A, which we set to 0. Our 17 will represent B, which we set to 4. We're going to be incrementing something by 1. So I'm going to use register 18 to help us out with that. And just like with the if statement, we're going to need a couple of text segment labels. I'm going to call the first label loop test, And then I'm going to call the second label loop end. Okay, so as the name suggests, the loop test will implement the test in our loop, our while loop. And we want to loop while A is less than B. And so we're going to compare A and B, R16, R17. And I could actually get this to work with a branch less than command, but instead it's going to be slightly more efficient for me to use the branch greater than or equal to command. So basically, these two commands are going to loop while A is less than B. So we're going to jump to loop end only when A is greater than or equal to B, or the A less than B condition is not satisfied. So if A is less than B, our branch statement is not satisfied, and then we can, on the very next line, put the code that is executed inside our while loop, which is just A++. So we're going to add 1 to R16. And then we want to sort of test again, right? Like we want to keep executing the while loop over and over and over again. And so in order to, re-execute our while loop, we're just going to jump back to loop test. And that's it. So as long as A is less than B, the branch greater than statement is not going to trigger. And we're just going to add we're going to add 1 to A and then jump right back to loop test and do it all over again. Once we hit loop end, the last thing we need to do in our program is just zero the variable A, and I'll just write that in there. And that's it. That's our complete program. So let's put a watch statement in there. We don't care about register 19 in this particular case. Build, run. All right. So A is equal to 0, B is equal to 4. A is not greater than or equal to B. And so we're going to compare. Our branch statement is not going to trigger. We're going to add 1 to A. And A is now equal to 1. And we're going to hop back up to the compare statement. Again, interesting to take a look at program memory at our code. So branch greater than loop end. The binary machine language instruction is F41C. So the offset for jumping over the while loop and getting down to loop end is embedded in F41C. And if we look at jump loop test, again, the jump command is a 32-bit command where instead of using an offset, the actual address is embedded in jump. And we can see that the address embedded in our jump command is 63, which corresponds to up here, the start of our loop, the compare statement, which is the first statement in our while loop. And so we can just keep executing. A is equal to 2 now. A is equal to 3 now. Now A is equal to 4. So A is no longer less than B. So our branch statement is going to trigger. We're going to hop down to the end. We're going to set A back to 0. And our program is finished. And so again, just like all of these lectures, make sure that you have been typing in these programs. Make sure that you're running these along with me. And definitely take a look at the instruction memory or program memory tab here. Make sure that you can kind of understand what's going on in the opcode column. Make sure you've got your AVR instruction manual open and you're looking at the jump command and the branch greater than commands to make sure that these values make sense to you. And just go slow, be careful. notice details. This is not sort of like a messy kind of high level thing that you can kind of skate your way through with like big picture concepts. This is obviously a very detailed kind of thing, and it pays to take your time and just go step by step.